All right, we're continuing with Chapter 4 of the Calculus textbook. In this video, we're going to go through Section 4.4, which is on indeterminate forms and L'Hopital's rule. So L'Hopital's rule is a technique for performing limits. If you have a limit problem, it might be either very hard to solve or not possible. But if you know L'Hopital's rule, that's a tool that you can use to solve a limit. And it's a really powerful tool. It's very easy to implement, and it involves using differentiation. That's why it's considered an application of differentiation. And so we'll talk about how to use L'Hopital's rule in a second. But this section is also on indeterminate forms. And so it's referring to indeterminate forms of limits. Now, indeterminate forms is also a really important topic for us to go over in calculus. And the reason is because, when it comes to limits, yes, as I've mentioned, as we've gone through this course, the main purpose of limits is, and the reason we learn them is because a limit is the foundational, fundamental concept of what a derivative and what an integral is. So we learn limits so that we can have that fundamental intuition behind what a derivative and what an integral is, and also so that we can understand what the definition of the derivative is and what the definition of the integral is. But in practice, you don't really use limits much, because the main purpose of calculus is when you're done with calculus, you know all of these differentiation rules really well. So you can have any function, any equation, and you can take its derivative really quickly and easily. And it's a similar idea with integrals. You never get into you don't use the limit. The limit doesn't come into play. The main purpose of calculus is so you can find derivatives of functions and equations and integrals of functions and equations quickly. Okay, and that's true. However, as we've gone through Chapter 4, what should have become apparent to you is that you can use limits for applied calculus, for applying calculus in real life. There are some uses for limits. So you're not going to, for applied calculus, you're not going to just completely forget about limits and never use them and only just remember the concept of a limit in your head. No, we've seen examples of how you can use limits, to analyze functions, to analyze equations. There was an example problem in Chapter 2 where there was like a function based on the theory of relativity, something like that, and we took the limit as one of the variables went to infinity. And what we found was that the whole function approaches, as that variable goes to infinity, the whole function approaches the speed of light. That's very interesting, right? That's a way that you're using a limit to analyze a function. We've seen when we're curve sketching, analyzing the shapes of graphs, we use limits to draw the graph, but as I've talked about, you can use limits to analyze the function. Limits really come into play if you've got discontinuities or points where maybe the first derivative doesn't exist, or even endpoint behavior. So the endpoints of for a logarithm is defined from 0 to infinity. So you might take the limit as x approaches 0 from the right of the logarithm, or a function with a logarithm. Taking limits as functions approach discontinuities or places where the first derivative doesn't exist or the second derivative doesn't exist. You could take limits as x approaches values of the function or of the first derivative or of the second derivative. These are all ways you can analyze functions and equations using limits. And so what I'm trying to illustrate is that it is valuable from an applied calculus standpoint to know how to evaluate limits, know how to take limits, to understand limits. It's not just purely you learn limits so you understand what the meaning of a derivative is and the meaning of an integral is, and then you just forget about it after calculus. Not really. Okay, and so with that this indeterminate forms here that we're going to learn, this is valuable for understanding certain types of limits, but just it's an angle that you could potentially analyze certain functions. That when you take limits, if you're evaluating a limit, there might be these indeterminate forms, and you have to understand how to deal with these forms, and you have to understand what they mean and why they're indeterminate. So this is really valuable for just understanding how to analyze functions. So let's get into this. All right, suppose we are trying to analyze the behavior of the function f of x is equal to the natural log of x over x minus 1. Although f is not defined when x is equal to 1, we need to know how f behaves near 1. In particular, we would like to know the value of the limit. Yeah, so if you're trying to analyze this function, so you want to analyze the behavior of this function. When x is equal to 1, you're dividing by 0. You're dividing, this is approaching, the denominator is approaching 0. The numerator is, natural log of 1 is equal to 0, but the denominator is equal to 0 as well. You can't divide by 0, so the function is not defined. But as we've done in the curve sketching example problems, you can analyze where functions aren't defined. You can take limits as x approaches that undefined value from the left and the right. A lot of times when you're dividing by 0, what we've seen, when you have a dividing by 0 situation, what you end up with is you take the limit as x approaches that value where the denominator goes to 0 from the left or the right, and that limit goes to infinity. You end up with a vertical asymptote. That's one thing you commonly see in a situation like that. But what they're pointing out here is that, so as x approaches 1, the denominator approaches 0, but as x approaches 1, the numerator also approaches 0. So you can't necessarily say that's a vertical asymptote. The only time you call that a vertical asymptote is when the numerator is approaching something that's not 0. So you're getting like a finite non-zero number, or not infinity either. If it was approaching infinity, that would be potentially indeterminate, but it's approaching some finite value that's not 0. So you're getting like 5 divided by 0. That's going to infinity. And so if you think about this limit, we can't say, okay, if we had the limit as x approaches 1 of x minus 1 over x squared. Okay, plug in 1, you get 0 in the denominator, 1 in the numerator, 1 divided by 0, that's going to infinity. The answer here would be infinity. Okay, we've done a bunch of limits just like that. That would be a vertical asymptote. But we can't do that here. We can't say, we plug in 1, you get 0 in the denominator, but the natural log of x is natural log of 1 is 0, 0 in the numerator, 0, so we're approaching 0 in the numerator, 0 in the denominator. That's indeterminate. We can't say what that's going to be. It could be infinity, but it could be, we don't know. It depends on how fast the numerator is approaching 0 relative to the denominator. Maybe that limit is 0. Maybe that limit's infinity. Maybe that limit is some compromise in between, right? So if you have a limit, if you're taking a limit of a quotient and the limits of the numerator and the denominator are approaching 0, that's an indeterminate form of type 0 over 0. Okay? The idea is you have the limit as x approaches a of f of x over g of x. If the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x is 0, then that's an indeterminate form of type 0 over 0, right? Now it says we met some limits of this type in chapter 2. For rational functions, we can cancel common factors. So this was, okay, look here. This limit. If you plug in 1, you get 0 in the numerator. Plug in 1 in the denominator, you get 0 in the denominator. But what we did was, when we came across these types in chapter 2, we could simplify it. Cancel out these x minus 1s, and you get x over x plus 1. Plug in 1, 1/2. Done. Okay? So but you see, that's interesting, right? That this doesn't go to, you have 0 over 0, right? From the start, if you plug in 1, if you take the limit of the numerator as x approaches 1 and the denominator, you get both are equal to 0. But the limit ends up being 1/2. That's interesting. It's not infinity. Even though you're dividing by 0, it's not necessarily infinity. Okay? Here, we used a geometric argument to solve this limit. The limit as x approaches 0, a sine of x over x is equal to 1. We have to use a geometric argument to prove this limit. But we'll see with L'Hopital's rule, this is easy. But these methods do not work for limits such as 1. So in this section, we introduce a systematic method. So what they're saying is we used a geometric argument here. Here we simplified, but we don't have a method for this. We can't simplify. We can't really use a geometric argument, so we need another way to solve this, right? This indeterminate form here, we simplified to solve it. This indeterminate form here, because sine of 0 is 0 and then x is equal to 0, this indeterminate form of type 0 over 0, we use a geometric argument to solve it. But the natural log of x over x minus 1, the limit as x approaches 1, we don't have a way to solve it. So we're going to introduce this. To solve that, we're going to use what's called L'Hopital's rule for the evaluation of indeterminate forms. Like we've only saw one indeterminate form so far, the indeterminate form of type 0 over 0. Another situation in which a limit is not obvious occurs when we look for a horizontal asymptote of f and need to evaluate the limit. Okay, so what they're saying here is we're taking now the limit as x approaches infinity, not 1. That's when you're looking for a horizontal asymptote, remember, you're taking a limit as x goes to plus or minus infinity. It isn't obvious how to evaluate this limit because both the numerator and the denominator become large as x approaches infinity, right? If we plug in infinity here, you get infinity over infinity. And what it's saying, this is not equal to 1. Infinity, cross out infinity, infinity, and get 1. No. It depends how fast is natural log of x grow relative to x minus 1. There's a struggle between numerator and denominator. If the numerator wins, the limit will be infinity. If the denominator wins, the answer will be 0. Or there may be some compromise, in which case the answer will be some finite positive number. Yeah. So in general, if we have a limit of the form, the limit as x approaches a of f of x over g of x, where both f of x approach infinity or minus infinity and g of x approach infinity or minus infinity, then the limit may or may not exist and is called an indeterminate form of type infinity over infinity. Okay, so here's another indeterminate form. We just saw the indeterminate form of type 0 over 0. Here there's an indeterminate form of type infinity over infinity, but it could be any mix of plus or minus infinity. It could be minus infinity over positive infinity over minus infinity over minus infinity, whatever. Any kind of infinity over infinity. We saw in section 2.6 that this type of limit can be evaluated for certain functions, including rational functions, by dividing numerator and denominator by the highest power of x that occurs in the denominator, right? So we saw how to solve certain types like this. If you, as x approaches infinity, you plug in infinity, you get infinity over infinity. And we used techniques to solve limits like this. We divided the numerator and denominator by x squared and got 1/2. But similar to what we just saw with 0 over 0, this method doesn't work for this limit. We don't have a method for that. But L'Hopital's rule also applies to this type of indeterminate form as well. So we can use L'Hopital's rule for indeterminate form of type 0 over 0 or indeterminate form of type infinity over infinity. Okay, so what is L'Hopital's rule? Suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. All right, so that's a lot of math jargon. We'll come back to that, okay? Suppose that the limit as x approaches a of f of x is equal to 0 and the limit as x approaches a of g of x is equal to 0, or that the limit as x approaches a of f of x is equal to plus or minus infinity and the limit as x approaches a of g of x is equal to plus or minus infinity. In other words, we have an indeterminate form of type 0 over 0 or infinity over infinity. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, assuming that this limit exists or is equal to plus or minus infinity. Okay, so f and g have to be differentiable. If they're not differentiable, then you can't do this. G prime of x can't be equal to 0 because then you can't evaluate this limit. All right, so we're not going to get into the math details of this, the fine mathematical details of this too much. The main idea is that if you can have an indeterminate form of the type 0 over 0 or infinity over infinity. Now notice it's not saying infinity over 0 or 0 over infinity. Well, okay, if you had in that case, well, okay, so why doesn't it say that? Well, all right, if you had a limit of where the numerator approached 0 and the denominator approached infinity, well, that limit's going to 0. This limit's going to be equal to 0. Okay. Now, what if you had a limit of the form where the numerator is going to some infinity, plus or minus infinity, and the denominator is going to 0? Where you're dividing a huge number by a very small number. That's going to some infinity. So those aren't indeterminate forms, okay? That's the thing. We're just talking about indeterminate forms here. So if you have an indeterminate form of type 0 over 0 or infinity over infinity, and it's any mixture of infinities, positive or negative, if you have that kind of indeterminate form, then what you can do is you can just take the derivative of the numerator and the derivative of the denominator and evaluate that. That's the same. You haven't changed the limit. The limit as x approaches a of the f of x over g of x, if these conditions are met, is equal to the limit as x approaches a of f prime of x over g prime of x. That's L'Hopital's rule. Okay? I'm not going to get into, they're saying if the limit on the right exists. I'm not getting into all that. All it's saying here is that if you have a limit and you evaluate the limit and you get an indeterminate form of type 0 over 0 or infinity over infinity, then you can take, without changing the limit, you can take the derivative of the numerator and the derivative of the denominator and have a new limit, where the limit as x approaches whatever you were originally working with is of the derivative of the numerator divided by the derivative of the denominator is equal to the original limit. That's it. That's L'Hopital's rule. And that there's no exceptions or certain reasons why it doesn't apply. That's it. This is universal across the board. I'm going to say it again. So this is universal across the board. If you have any limit, and we'll see you might say, well, what is A? What can A be? A can be anything. We'll see that in a second. Any limit where x approaches something and you have a function of x divided by another function of x. That's the limit you're evaluating. If you evaluate that limit and you get an indeterminate form of type 0 over 0 or infinity over infinity with any mixture of infinities plus or minus, doesn't matter. That's an indeterminate form, and we talked about why it's indeterminate. You can't say what the limit is. And to simplify that limit, what you can do is you can change that limit to where it's the limit as x approaches whatever the original number was of the derivative of the original numerator divided by the derivative of the original denominator. And that could potentially simplify that limit so you can solve it. Okay, and then again, you might say, well, what about 0 divided by infinity or infinity divided by 0? Those aren't indeterminate forms, and I just talked about why. Those you can just solve it. Okay, so, but again, as it says here, it's important to verify the conditions regarding the limits of f and g before using L'Hopital's rule. You have to have one of those two types of indeterminate forms, is what they're saying here. You have to have an indeterminate form of type 0 over 0 or infinity over infinity, or else you can't use L'Hopital's rule. Okay, now here's another important note. L'Hopital's rule is also valid for one-sided limits and for limits at infinity or negative infinity. So you might be wondering, well, okay, can you apply L'Hopital's rule? For what values of which x is approaching can you apply L'Hopital's rule? Anything. It could be a one-sided limit. It could be an infinite limit. Really cool, right? Now, here they talk about, they try and give an explanation on why L'Hopital's rule works. I'm not going to get into this. It's not even a full explanation. We have to go to Appendix F to get the full explanation. But this is kind of like a proof of L'Hopital's rule, but you can pause the video and take a look at this if you want. Okay, and so now what they do here is they come back to that original problem that we started with at the beginning of the chapter. You plug in 1. You get natural log of 1 is 0 divided by 1 minus 1 is 0. So that's an indeterminate form. Pretty much what you're taking the limit as x approaches 1 of this and dividing that by the limit as x approaches 1 of this. We know that that's a property of limits. We can do that. But you get the indeterminate form of type 0 over 0. So you use L'Hopital's rule. 1 over x divided by 1. Limit as x approaches 1 of 1 over x is equal to 1. Boom. Really easy, right? What is that saying? That means that the natural log of x, as x approaches 1, approaches 0, because natural log of 1 is 0, at the same rate that x minus 1, as x approaches 1, approaches 0. That 0 divided by 0 is like the same number, right? It's kind of like infinity divided by infinity could be equal to 1 if you have the same infinity. But infinity is not a number, but in a certain circumstance, they could be the same infinity based on if you have a specific circumstance. Like here, for example, the limit as x approaches infinity of e to the x over x squared. Okay, plug in infinity, you get infinity over infinity, but e to the x rises at a much faster rate than x squared. Exponentials increase much faster than, like variables squared. Exponentials increase very fast. And so this just goes to infinity, right? You get infinity over infinity, but this is not equal to 1. This infinity is for if you plugged in x is equal to 1,000,000, you're going to get a huge value compared to e to the 1,000,000 is much larger than 1,000,000 squared. Okay, but so we saw problems where we analyzed it the way I just talked about it. We analyzed it that way, so we could have just figured out that this is going to be equal to infinity on our own without L'Hopital's rule. But with L'Hopital's rule, it's easy. E to the x divided by 2x, and then e to the x, and then you do L'Hopital's rule again, e to the x divided by 2. Okay, well, there you go. The limit as x approaches infinity of e to the x divided by 2 is equal to infinity. Okay, limit as x approaches infinity of natural log of x over square root of x. You get infinity over infinity. They do use L'Hopital's rule, but what you get is another indeterminate form of type 0 over 0. 1 divided by infinity is 0. 1 divided by 2 times the square root of infinity, it goes to 0. So you have this indeterminate form of type 0 over 0. You could use L'Hopital's rule again, but instead you can just simplify this. And what you get, you simplify, you get 2 over root x, and that is, as x approaches infinity, that goes to 0. Okay, and so this was the opposite of the previous example. The natural log of, or the square root of x increases, as x goes to infinity, this increases faster than natural log of x. So the denominator outpaces the numerator, so this limit goes to 0. Okay, here's another example. Tangent x minus x goes to 0. X cubed goes to 0 as x approaches 0. So they use L'Hopital's rule, take the derivative. We still have an indeterminate form of type 0 over 0, so we use L'Hopital's rule again. Then they use a technique here. They separate this out to get this limit, and then this limit as x approaches 0 of tangent of x over x. And then you can take advantage of trigonometric limits, it says, or you could just continue using L'Hopital's rule. So to me, as just for applied mathematics, like for engineering, you just want to use L'Hopital's rule as much as you can. So to me here, secant squared, the limit as x approaches 0 of secant squared of x is equal to 1, but as x approaches 0, the limit of tangent of x is equal to 0, so this is going to go to 0, this is going to go to 0, so you could just use L'Hopital's rule again, and you'd get rid of the denominator. And so this is like mathy stuff, using trig integrals. You could just use L'Hopital's rule here again, you'd get rid of the denominator, and then boom, then you're done. I mean, it might be a little complicated taking this derivative, but just plug that into your calculator, right? The derivative of 2 secant squared x tangent x. But still, you're going to get rid of the denominator because 6x is going to go to 6. But they talk about, they use another way where they separate this into like a trig integral that you know, and then they know that this limit is equal to 1/3, so it's kind of mathy stuff. All right. Here's a one-sided limit. You can use L'Hopital's rule. And it says, well, okay, it says if we blindly attempted to use L'Hopital's rule, we would get this. But that's wrong. And why is it wrong? Because this is not, if we look here, it's not, if you plug in pi, you don't get an indeterminate form of type 0 over 0 or infinity over infinity. The numerator approaches 0 as x approaches pi, but the denominator does not. So you can't use L'Hopital's rule. So it's just pointing out you have to make sure the conditions are satisfied to use L'Hopital's rule. This was just a direct plug-in. If we just did a direct plug-in, you'd get 0 over 2. 0. Okay. Indeterminate products. So we just went over these two indeterminate forms. And I explained why they're indeterminate. And and again, this is not indeterminate. These two are not indeterminate. So we've just gone over two indeterminate forms so far. Now we're going to go over some more. Indeterminate products. So if the limit as x approaches a of f of x is equal to 0, and note that this a, it's universal. We're at the limit as x approaches a could be anything. A one-sided limit, an infinite limit, whatever. If the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to infinity, or negative infinity, then it isn't clear what the value of the limit as x approaches a of f of x times g of x, if any, will be. Okay, so if you have any limit as x approaches anything, one-sided whatever. You plug it in and you get one portion of the limit being evaluated is 0, and it's being multiplied by another portion that's going to infinity or negative infinity. You might think, oh, well, this is 0. No, this is indeterminate. You can't say for sure what this is in the same way that you couldn't say for sure what 0 over 0 or infinity over infinity was. Because it says, look, if this is f and this is g, there's a struggle between f and g. If f wins, the answer will be 0. If g wins, the answer will be infinity or negative infinity. Or there may be a compromise where the answer is a finite non-zero number, right? It depends on how fast is this approaching infinity. How fast is this approaching 0? If this is approaching 0 much faster than this is approaching infinity, then this whole limit will go to 0. If this is approaching infinity or negative infinity much faster than this is approaching 0, then that limit will go to negative infinity or positive infinity. Or there could be a compromise where you get like a finite number. This kind of limit is called an indeterminate form of type 0 times infinity. We can deal with it by writing the product f times g as a quotient. So what you do is, so if you have f times g, and so the limit of f is going to 0 and g is going to infinity or vice versa, what you do is you write it as a quotient, f divided by 1 over g, or g divided by 1 over f. And what does that do? That converts it into an indeterminate form of type 0 over 0 or infinity over infinity so that you can use L'Hopital's rule. That's it. So you have to memorize this. If you have an indeterminate form of type 0 times infinity, then just write it as a quotient so that you get an indeterminate form of type 0 over 0 or infinity over infinity, and then from there you can use L'Hopital's rule. That's how you solve these. So here, the limit as x approaches 0 from the right of x times natural log of x. What do you get here? 0 times the limit as x approaches 0 from the right of natural log of x is negative infinity. That's a 0 times infinity indeterminate form. Okay, so what do? They write this as x times natural log of x. They write that as natural log of x divided by 1 over x. Now you can use L'Hopital's rule. You get 1 over x divided by minus 1 over x squared. That simplifies to minus x. Plug it in, you get 0. Okay? Now, that's how you solve it. Now, it notes, though, that in solving this example, another possible option would have been to write it this way, right? You bring the natural log of x into the denominator, which also gives an indeterminate form of type 0 over 0, but you apply L'Hopital's rule, and you get a more complicated expression than the initial one, so you can't solve it. And so it says, in general, when we rewrite an indeterminate product, we try to choose the option that leads to the simpler limit. Okay? So if that's not obvious, then you just might have to try both ways. You might bring one of the products into the denominator. It makes it more complicated. Then just try the other way. Okay. Indeterminate differences. We saw some example problems like this in Chapter 2. And these are indeterminate forms of type infinity minus infinity. Okay? You can't, this is not necessarily equal to 0. You don't know what this is. Okay? Now, just note that, what about this? That's not indeterminate. This is equal to infinity. Okay? Like, and you know, kind of similarly, this here. This is not indeterminate. This is going to be equal to infinity, and you could put pluses or minuses. It doesn't matter. This is infinity. So just note, we're just talking about indeterminate forms here. Okay? So this is indeterminate. And so why is that? Because you don't know. Infinity is not a number. It's not a specific number. It depends on how fast is this approaching infinity and how relative to how fast this is. You could get, this could be equal to 0. This could be equal to infinity. This could be equal to some finite number. And we saw, you know, there was examples where we saw like the limit as x approaches infinity of x squared minus x. Right? That's infinity minus infinity, indeterminate. We did an example like this in Chapter 2. In general, what you want to do is you want to try and rearrange the equation to get a determinate form. So you'd factor out a x here. Now you plug in infinity. You get x infinity times, then infinity minus 1 is infinity. So you get infinity times infinity. That's not indeterminate. That's equal to infinity. Enormous number times enormous number gives another enormous number. And what's happening is the x squared is increasing much faster than x squared is increasing faster than x. So this is going to infinity. And the idea is if you plugged in 100 billion, if you did 100 billion squared minus 100 billion, you're going to get some enormous number. That's the idea. All right. It says if there's a contest between f and g, will the answer be infinity or negative infinity, or will they compensate or compromise on a finite number? To find out, we try to convert the difference into a quotient. For instance, by using a common denominator or rationalization or factoring out a common factor so that we have an indeterminate form of type 0 over 0 or infinity over infinity. So, yeah, okay, this was the method that we used before. We didn't convert this into a quotient. And you do it like this if you can, but the more general way to do this, to solve this, is similar to what we just saw for the indeterminate products, 0 times infinity. You're trying to convert it into a form. In general, if you're trying to solve an indeterminate form limit, in general, what you're going to be doing is you're going to be trying to convert it into a form where you can use L'Hopital's rule. Okay, so we saw L'Hopital's rule was applied for the 0 over 0 or infinity over infinity type. Then we looked at indeterminate products, 0 times infinity. To solve that, in general, we convert it to a quotient to where we can use L'Hopital's rule. And that's in general what we're going to do here too, with indeterminate differences. But just pointing out, you can always just look to start, but you can look and see, maybe I can just put it into a form where it's not indeterminate without having to use L'Hopital's rule. Sometimes you can do that. But in general, you're going to want to solve it, you're going to want to be putting that indeterminate form into a form where you can use L'Hopital's rule. So here, right, you plug in 1, you get 1 divided by 0, so that's going to infinity, minus 1 divided by 1 minus 1, that's going to infinity. So you have infinity minus infinity. And so, okay, so what they do is they combine these fractions, and they do the subtraction. They get this, right? With common denominators, they get this. Plug in 1, what do you get? The limits are going to 0 in the numerator and the denominator. So you can use L'Hopital's rule. Using L'Hopital's rule, you get this. Simplify, you get this. Again, we have an indeterminate form of type 0 over 0 here as well. So we apply L'Hopital's rule again. And applying L'Hopital's rule the second time, you actually get to a form where you can plug in 1 and get a number. Done. Okay. Here, calculate the limit as x approaches infinity of e to the x minus x. That's infinity minus infinity. And so what they do is it says, yeah, so you would expect this limit to go to infinity because you know that e to the x it rises much quicker than x, but they illustrate the technique here. And so they factor out an x, and with that, you plug in infinity and you get infinity times minus 1. Isn't that right? Oh, no, you get infinity. The limit as x approaches infinity of e to the x over x is infinity. So you get infinity times infinity. So it's kind of like what we did here. They just put it in, they factored something out to put it into a form where you get a determinate form for the limit. So here they didn't use L'Hopital's rule. They didn't rearrange it, combine fractions or something to use L'Hopital's rule. So you can, in general, you're going to want to put it into a form where you can use L'Hopital's rule, but you can go any route you want. Just rearrange the limit so you can get a form that's determinate. All right, now, just to point this out, you might be saying, well, what about 0 minus 0? That's not indeterminate. This is going to be 0. What about infinity minus 0? This is going to be infinity. Okay, indeterminate powers. Several indeterminate forms arise from this limit. The limit as x approaches a of f of x to the g of x power. Okay, so here's 3 different indeterminate forms. So 0 to the 0 power, infinity to the 0, 1 to the infinity. So you can think about it on your own why these are indeterminate. But then you can also think about on your own why 0 to the infinity is not indeterminate. Okay, now note that you might say, well, okay, it gives plus or minus infinity as an option, but it doesn't say plus or minus infinity here. Well, that won't apply here. So if you have minus infinity to the 0, this is in its own like world over here with the minus sign out front, right? And then now if you had like minus infinity to the 0, then it would be a similar type of analysis as shown here. I think they don't want to introduce confusion by putting a minus sign here, because it depends on, okay, are you talking about minus infinity to the 0 or putting this in parentheses? This here is going to be this same type, this infinity to the 0. Okay, this is going to be this will be this same type. This is just, you could just analyze this on its own. You could bring the minus sign out in front of the limit. Okay, so if you've got one of these types of indeterminate forms, okay, and here, but you can have, they indicate explicitly that you can have 1 to the plus or minus infinity. All right, but how do you deal with these? One of these types of indeterminate forms. Either you take the natural log, so here's the entire function. It's like y is equal to this f of x to the g of x. You take the natural log of both sides. Or you write it as an exponential. So f of x to the g of x power can be written as e to the g of x times natural log of f of x. And so if they give an example here with that, they have this function here. It's 0 to the infinity in indeterminate form. So they write this as y is equal to the function. Take the natural log of both sides. And then now you take the limit of both sides as x approaches 0. And you're able to use L'Hopital's rule here. And with L'Hopital's rule, you get 4. Now, what that's saying is that we've computed the limit of the natural log of y, but we want the limit of y. So to find this, we use the fact that y is equal to e to the natural log of y. And so you get that the limit is equal to e to the 4th power. All right, so we're going to do a bunch of example problems so you can get a feel for this. Okay, but that's indeterminate forms in L'Hopital's rule. Let's now work some example problems.